to touch on. First of all, well, let's step back a bit. All right, as you've just heard from my introduction, I've worked in many parts of the world, and one of the things I first noticed when I came here to the Mountain West and to Colorado was these yellow-red piles of rock waste, mining waste. They're the legacy of 150 years, up to 150 years of mining here in the Mountain West. You don't see those in other parts of the world. I could go to Western Tasmania, which is also a historic mining area, or Austria, as I'll show pictures of later, and you're actually struggling to see mines. You're actually struggling to see where the historic mines were. So there is something going on here, and that brought me to the first question. I mean, how long will the environmental legacies of past mining last, and what controls that? And then also, just because of what this conference is about in part, I'm going to ask the question, what will the legacy of future mining be? And almost argue that obviously there will be future mining at some time here in the San Juans. So I'm going to try and be dispassionate. So those are the two questions, which I'm essentially going to show the evidence for, discuss. So let's, oops, wrong way. There we go. So a quick reintroduction to the environmental legacies of hard rock mining. One thing that we're not discussing here, but it is important and is considered important worldwide, is just the disturbance of ground and how to minimize that, how to deal with that. Obviously, we're more interested here in the water quality impacts of hard rock mining. So a nice simple way which I use with my own students, why is there a problem with hard rock mining? In a kind of trite way of saying it, we break rock up in a mine, we bring it to the surface, and then we just leave it there. And by doing that, we expose it to oxygen and to rainwater, to snowmelt, and that causes rapid weathering. Some of the weathering reactions that Doug has been talking about, the mineral reactions, and it's those reactions which actually impact the water quality, the release of metals, the release of acidity. We could also argue it's the same thing that's essentially happening in a mine adit. We're opening up the rocks to exposure to oxygen and water and percolating surface-derived water, and it's the reactions which then take place in the mine adits, in the adjacent rocks along fractures, which give you the red coloration of the water that is emitted from the mine. So that's in essence what we're doing and why mining is so important as an environmental issue. So just again to reiterate, the most important reaction which we're dealing with when we're looking at the most important chemical reaction, this weathering reaction, is the weathering reaction of pyrite, the iron sulfide. So the reaction is actually, a version of the reaction is written down here. You take pyrite, iron sulfide, you add oxygen and water. In the end, you produce the iron hydroxide, or it can be other minerals, the red coloration, which you see on many creeks or on the surfaces, for instance at Red Mountain, and also produce sulfuric acid. And this reaction is actually used commercially to produce sulfuric acid in many parts of the world. This is how you actually produce sulfuric acid and how historically it's been produced. So the point is that for every mole of pyrite, you're actually producing 4 moles of acid when you weather it. So it's a very potent source of acidity, and it's this reaction which actually gives rise to about 95% or maybe even higher than that of the acidity in mining districts. So that's the reaction we're interested in, and just run through some of the background points here. Pyrite is a widespread mineral throughout many rocks. Typically, relatively low concentrations, so I put 0.1%, that's kind of average. However, it's the most abundant sulfide mineral in most metal ores, running, say here, anywhere up to 50%. There are mines in northern California, for instance, where you've got more than 50% pyrite, and the water draining those mines, or that was draining the mines before rehabilitation, was negative. Essentially, it's concentrated sulfuric acid. And pyrite makes up about 5% of the rock, which is mined as ores in the San Juans. So and then just again, saying in a slightly different way from Doug, so low pH, commonly less than 3 for groundwater, streams and soils, soil water, where we've got mined ground. And because of the acidity, other minerals in the rock weather faster. And because also ores, by definition, are rocks with high concentrations of many metals, otherwise we wouldn't mine them, you're going to weather the minerals which hold those metals and hence release those into the environment. And some of the metals, which are obviously metals and metalloids, which are released and are of environmental concern, are aluminium, arsenic, cadmium was mentioned as well, so a whole series of metals. So in essence, where we've got acid drainage, we've got high concentrations of many metals in any water. So, and just to say in a slightly different way again, we separate acid mine drainage, where it's anthropogenic. So we're essentially bringing the pyritic rock to the surface, or opening up an adit, letting the pyrite weather. So that's our mine impact. But here in the San Juans, we're also acutely aware of the fact that there are also natural sources of acidity. So Red Mountain here and the iron hydroxide precipitates on the surface. That's natural production of acidity, which Doug has been talking about. So the question essentially I want to start with asking is, when will acid production stop if we've got a pile of mine waste rock, something like this? And the trite answer to that is, yes, it will naturally ameliorate once all the pyrite has been weathered and reacted out. So eventually that acid production will stop. And obviously the question is, when will that take place? We can also rehabilitate, reclaim the land, which we'll be hearing about through much of the rest of this conference. So, and that was the question which essentially I was interested in when I came here and when I first saw these yellow piles of rock. So a simple way of looking at it, pyrite concentration decreases with time because of the fact that you're reacting out the pyrite because of the weathering. Once it's gone, it's no longer, well, not 100%, but approximately it's no longer going to produce any acidity. And the pH is a function of the rate of pyrite oxidation in a rock mass. So pH will steadily rise as the amount of pyrite in that rock decreases. So that's what's shown schematically in this diagram. So the pyrite concentration in the black decreases with time. The pH will rise with time because you're reducing the rate of reaction out of that pyrite. So obviously the question, one of the questions here is, what's the scale? How long is this going to take if we just have a natural acid producing or an anthropogenic acid producing site? We can obviously remediate, and that's what I said a lot of the talks will be about today. And essentially what you're doing, again from a nice simple geological perspective, you're reducing water and oxygen access to pyrite-rich rock when you remediate a mine site. There's various ways in which you can do that. You can obviously, this example here of a waste pile in which you cover it, allow vegetation to grow. Essentially what you're doing is reducing the input of oxygen and water from the surface. Hence, you're reducing the rate at which the pyrite reacts. Or you can plug up a mine adit. Essentially, you're doing the same thing in terms of the chemistry. But there's an important point here to remember, which you'll realize when I run through this, is significant. If I go to the same schematic graph, which I had yesterday, which I had in the last slide, if you're remediating, there's the line of pyrite without remediation. If you're remediating, this is your line of how pyrite's going to decrease with time. All right, you're essentially stopping the reaction or reducing its rate down to almost nothing, but the pyrite's still there. And remediation assumes long-term engineering integrity. Because if you break, for some reason, something happens, and you break that seal for oxygen and water, then the pyrite's there to start weathering again, and you're going to produce high acidity once again. Now, whether that's important depends obviously on how long these reactions are actually going to take place. So, when will all the pyrite be reacted out? And the answer is that it depends on many factors, and we don't really know. So just run through some of the factors here, which we expect it to be related to. So the grain size and form of the pyrite, the fragmentation, the amount of fragmentation of the rocks, the amount of water infiltration and oxygen infiltration, and also, importantly, climate. So that comes back to the point I made at the beginning. In all the places I've worked in the world, I've never seen these yellow piles before I came here. So something is happening here, which is different, which is related to the mountain climate. So that's what I had a project which was partially supported by the Mountain Studies Institute a few years ago by student Jessica Duggan, who is now working for the EPA out of Denver. Essentially what she did was to try and get an estimate as to how long this acid production in these mine sites will last. And the way she did it was by comparing two geologically similar environments. Sugarloaf up in Leadville, so I'll show a picture in a minute. So that is a site where essentially mine waste has been sitting around for 100 years and has been undisturbed since. And also the Chattanooga iron fen, acid iron fen here just north, and comparing how far the reactions have taken place in those two sites, and making the argument that at Sugarloaf the rocks have been sitting at the surface for 100 years, at Chattanooga the rocks have been sitting at the surface for approximately 10,000 years. So just pictures, this is Sugarloaf, waste piles from 1880s mining, essentially untouched since. They are silver gold ores with a few percent pyrite. That's what waste piles look like, up at 11,000 feet or so, after 120, 130 years now. The environmental, how should we say, parameters at this site, what really surprised us right from the beginning is there is fresh, unweathered pyrite on the surface of these mine dumps. Nice and shiny. It hasn't reacted at all. The pyrite within the mine dumps has reacted, and there is minor secondary iron hydroxides. Ephemeral drainage from these mine dumps runs about pH 3, so very typical. And she did a mass balance as to how much pyrite was there and came to the conclusion that essentially more than 90% of the pyrite still remains in these mine dumps, even after 100 years. And then Chattanooga. So we have to do a bit of a geological interpretation as to why this is a 10,000 year site. So what we're actually looking at is the material which is producing acidity to the Chattanooga iron acid fen here. And that's essentially a talus slope at the base of this mountain, which I've forgotten the name of. And the talus is made of blocks of of mineralized volcanic rocks with silver and moly, and a few percent pyrite, largely with what Doug described, quartz sericite pyrite alteration. So very similar rock type. And what, as a geologist, I interpret this is a talus pile that was left after a retreat of the valley glaciers. So essentially that has been broken rock at the surface since the retreat of the glaciers, so between about 10,000 and 15,000 years, in essence. So that's obviously a picture of another place I've worked in the world. And in terms of the environmental parameters, so the pyritic tuff down here, this is what the rocks look like in microscopic view. Down here there is most of the this would have been a pyrite. Most of it has been overprinted, but a small proportion is still remaining. The groundwater seeps at the base of the talus slope have a pH between about 4 and 6, and that's what's feeding the acid fen here. And the estimate is less than about 1% of the pyrite remains. So about 0.5% of the pyrite. So over the 10,000 years or so, essentially 99% of the pyrite, approximately, has been reacted out. And we can model this. This is a kind of chemical approach, but don't worry about the details in total. It's the results that are important. So it's obviously time at the bottom. So there's Sugarloaf, there's Chattanooga. This is the kind of range at which this parameter, the amount of the proportion of pyrite remaining, will decrease with time. This is the pH increasing with time. So the pH starts at about 3. After about a few thousand years gets to 4. Over 10,000 years gets to 5. So essentially in this climate, what we're saying is that these, the acid production at a pile of broken rock on the surface will continue for, of order, 10,000 years until it totally reacts out. So the mine dumps, which we're seeing now, unless we do something about them, they will remain producing acidity for about 10,000 years. And this is obviously my kind of simplistic interpretation of what we will see in 10,000 years' time if we want to come back. So, see a picture of Red Mountain. So the mine waste rocks, they will still be producing mildly acidic drainage, maybe 1 or a bit more pH units higher than at present. And by analogy with what we see at Chattanooga, they'll probably be covered with grass-covered slopes. There'll be enough vegetation, enough soil to actually support grasses. However, the acid mine drainage from Red Mountain will still continue because natural processes, largely fragmentation of the rock by ice action, will keep fresh pyrite at the surface and keep that process going. So that's essentially the first part of what I want to say, but let's now go to the future and say a few things. Now, it was interesting hearing Terry this morning, but I'm going to take a slightly different approach to this. Future mining in the San Juans. Will it take place? Well, so this is obviously this is tonnages mined in San Juan since the beginning of the 1880 to 1991 when Sunnyside closed. And you've got what the experts on this issue of historic mining regard as a mining cycle, or 3 sub-cycles within that. And if we look at major mining districts in the old world, Central Europe, Central Asia, places like that, a major mining district of the same caliber as the San Juans always goes through multiple cycles of mining. In essence, mining is renewed, mining stops and then becomes renewed, or goes down to almost nothing and becomes renewed, because after new insights as to where ore is, or because of new technology. So if you think a mining field is mined out, the answer is almost certainly no. A major mining field, there is still ore underground and it can still be mined. So that's one aspect. There is plenty, anybody will tell you there's plenty of ore still to be mined here in the San Juans. It's a question of obviously finding it and economically mining it to renew mining. But another aspect or another viewpoint is just the increasing global demands for most metals. So this is a graph of copper production from the 1900s to the present. Now, I'm going to use copper because there's most data, although copper wasn't important here in Silverton, to illustrate these points. Now, much of that increase is just because of the world's population growth. However, obviously we expect it to continue at present. Much of it is also due to the increasing standards of living. So you've got those two factors. There's still ore here. There is increasing demand for all of the metals which we can mine here. What types of ores might we be looking at? What types of mines might we be looking at in the San Juans again? And Doug has gone through this. So he's mentioned the three main ones. They're porphyry type ores. I've given a couple of examples here. Climax Henderson, acid sulfate, gold silver ores. Again, example of Summitville. And then the vein ores, which I've given the local examples, the vein polymetallic ores, Sunnyside, Eldorado, Creed. And I've put a picture of Climax, a satellite image of Climax here, to emphasize one point, and that is porphyries are large ore bodies. They are mined on a large scale. This is Climax, the distance from there. This is Climax before rehabilitation. The distance from the mine, from the open pit to the mine's tailings dam here is about 6 kilometers. So it is these are really large systems, large impact mining compared to the vein ores which we're used to thinking about here in the San Juans. And I would argue that there's actually, if we were in Peru or Chile, this area will be covered in drill pads at present, exploring for ores in many parts of the mountains. Compared to Peru and Chile, there has actually been little systematic exploration at depth. And modern mining could easily go down to about 700 meters and be as economic as it is essentially at the surface. So there's plenty of potential. And then I'll also say a few things about what has happened in the mining industry since mining stopped here in the San Juans 20 years ago. So the increased production of the metals worldwide has actually been from a smaller number of larger mines. So here's the graph of copper production with time. At present, there are about 140 mines which are producing the vast majority of that copper. 20 years ago, when Sunnyside closed, there were about 250 mines. So the mining industry has become much bigger scale as a general rule. Where you've got a mine, it's going to be bigger, it's going to have a much larger impact. And that's what the major mining houses want. Essentially, they want large open pit bulk mineable reserves. They want large pits. And the bottom graph is actually only for Australia, but what actually turns out that because of these changes, the tonnage of material mined, and one of the lines here has disappeared. Oh well. So that this line here is the grade of copper ores over time from the 1840s to the present. And then this line is the grade, this line is the tonnage of rock mined, produced copper over the same period. There's been this astronomical increase worldwide of the tonnages of material mined to produce the metals which we use. Because of the combination of these factors, there's the mining large, bulk, mineable open pits as opposed to narrow, thin veins, and because of the increase in demand over time. Worldwide, there's been an astronomical increase in the actual tonnage of material that's mined worldwide. Why? Well, there's a number of reasons. Open pit mines are sought by the majors because of lower financial risk. For instance, the cheapness of haulage means that it's now possible to mine large tonnages, whereas in the past, essentially the major cost of a mining enterprise was labour. But that said, and obviously I'm probably frightening a few people here, just a vision of what the San Juans might look like in the future. That said, can these trends actually be continued? And there's a lot of argument amongst us, amongst the economic geologists, both in the industry and in academia, that the answer is no. That actually, perhaps, the future will see a return to smaller scale mining. And there are a number of factors which are driving that. There's been very few large tonnage quality resources discovered in the last 20 years or so worldwide. Sustainability concerns, especially with respect to land use. You are sterilizing enormous areas of land with these large mines. And then also higher energy, increasing energy prices will reduce the profitability of large tonnage mines. So there's a lot of arguments to say that we may be returning to an environment in which relatively small scale underground mines become much more profitable and much more what relatively small mining companies are actually going to go after and can exploit profitably. And I put down the bottom here some issues that we'll have to think about if that's the case. There's the environmental impacts of exploration. There's also community sustainability. Is it possible to actually have a mining industry in a small place like Silverton and sustain it over the years to avoid booms and busts? Because any small mine has a limited lifespan. And obviously, you've got to continue that. And lastly, just as to say, well, yes, what is best practice? Many years ago, I visited this place in Austria, Silverton, which is actually the world's largest tungsten-only mine. It's been running for almost 40 years. It's about double the size of what Sunnyside was in terms of tonnage. There's the mine. There's a picture of the mine. All right. So I'm being a bit unfair here, but that's actually if you go down to here and look that way, there's the mine portal. There's the national park. Sorry, this has been washed out a bit, but there's snow-covered mountains at the back and the national park at the top of that hill. This is best practice mining. So I'm actually standing at the office stairwell to take this picture. Much of the processing of the ore is underground, and that is the mine portal, the main crusher. The primary milling is underground. The ore is then taken by conveyor belt, similar as Henderson, down to the main valley a few kilometres behind me, and that's where the mills are. So this is the most of the waste rock is used for backfill. So this is what can be done as best practice, relatively small scale mining at the present. Thank you, Chris.